MBC Sensor Calibration. MBC Line-Following Sensor Calibration Instructions. Press the calibration button on the sensor to start a 5-second calibration process. During these 5 seconds, hold the sensor about 0.8 to 1 centimeter above the surface and move it back and forth across both black and white areas. During the 5-second calibration process, the indicator lights on the sensor will remain unchanged. At the same time, the sensor will automatically record the maximum, brightest, and minimum, darkest, grayscale values for each photodiode. If the sensor completely leaves the black line, the system will record the last detection point that was in contact with the black line. If you want a specific color to be recognized as white during calibration, let the sensor scan that target color along with the black area. The sensor will automatically identify the target color as white. If you want a specific color to be recognized as black during calibration, let the sensor scan that target color along with the white area. The sensor will automatically identify the target color as black. After calibration is complete, you can check the 8 indicator lights on top of the sensor to confirm whether it was successful. The calibration data is automatically saved in the sensor, so there's no need to recalibrate before each use. Recalibration is only required when there are changes in ambient lighting or usage conditions, such as adjusting the sensor's height or moving it to an environment with a different light source. Basic application. Get line black error. The sensor measures the distance between the robot and the center of the black line. The value ranges from -8 to +8, where a negative value indicates the robot is on the left side of the black line, and a positive value indicates it is on the right side. Get line black width. Detects the width of the black line by calculating how many sensors are currently over the black line. Get line white error. The sensor measures the distance between the robot and the center of the white line. The value ranges from -8 to +8, where a negative value indicates the robot is on the left side of the white line, and a positive value indicates it is on the right side. Get line white width. Detects the width of the white line by calculating how many sensors are currently over the white line. Next, let's take a look at the sensor's actual display. On the display, when the MBC sensor is on the right side of the black line, the value will show as positive. The farther the sensor moves from the line, the larger the absolute value of the positive number, up to a maximum of 8. Conversely, when the MBC sensor is on the left side of the black line, the value will show as negative. The farther the sensor moves from the line, the larger the absolute value of the negative number, up to a minimum of -8. The bottom of the screen displays the width of the black line, showing how many sensors are currently over the black line, ranging from 0 to 8. Basic line following. Application. We will use getLine black error and getLine black width to implement the line following function. By multiplying the getLine black error value by p, proportional coefficient, you can achieve a simple line following function. By adding d, derivative term, you can create a PD control, making the line following response smoother and more stable, reducing oscillations and overshooting. Next, let's take a look at the actual line following in action. GetLine black width can be used to determine whether the robot has reached a junction and can serve as a condition for executing a turn. Using only getLine black width is not sufficient for a stable judgment because the loop may exit prematurely before the line following has fully stabilized. Therefore, an additional motor angle check is added as a supplementary condition to ensure the robot does not interrupt the line following process before reaching the intended distance or position. Next, let's take a look at the actual line following in action on the screen. Intermediate application. GetLine Sensor 8 reads the reflective values of the 8 photodiode sensors, with each sensor output ranging from 0 to 100. The values read can be used for subsequent line following control, error calculation, or other applications that require precise light data, such as PID control, path prediction, and speed adjustment. Next, let's take a look at the sensor's actual display in action. On the screen, we can view and use the 8 photodiode sensor values read by GetLine Sensor 8. By retrieving the values from all sensors, these readings will be displayed in real time on the top of the EV3 screen when the program runs, allowing users to visually observe the changes in reflectivity for each sensor. The layout on the top of the EV3 screen is as follows. The first row shows the values of sensors 1 to 4, and the second row shows the values of sensors 5 to 8. Intermediate line following application. Next, I created a custom block that integrates sensor reading, value conversion, and error calculation into a single function. This not only makes the main program cleaner and easier to read, but also simplifies future maintenance and feature expansion. Within this block, the first step is to use getLineSensor8 to read the reflective values of the 8 photodiode sensors. Next, each sensor's reading is evaluated to check if it is below 50. If so, it indicates that the sensor has detected the black line, and the getLineBlackWidth count is incremented by 1. Finally, the system counts all sensors that detected the black line and outputs this total count to the main program for subsequent calculations or decision-making. Next, let's take a look at the actual line following in action on the screen. Advanced application. Next, we will integrate the line following program into a new custom block, while also including the motor angle calculation within the same block. The advantage of this design is that the motor angle values can be directly accessed for decision-making, making the program structure clearer and more modular, and simplifying subsequent conditional control or action triggering. The exit condition for the line following loop can be set as follows. When the motor angle reaches the preset value and getLineBlackWidth greater than or equal to 7, or when getLineSensor8 detects that sensor 1 or sensor 8 has contacted the black line, the loop will exit, ensuring that the program stably ends at junctions, the finish line, or other specific positions. This design allows for flexible monitoring of specific areas of the line. For example, you can use sensor 1 to detect a junction on the left and sensor 8 to detect a junction on the right. It can also be used for precise control of the parking position, enhancing the accuracy and reliability of line following decisions. Next, let's take a look at the actual line following in action on the screen. Thank you all for watching this tutorial. We covered everything from basic setup and sensor calibration, to intermediate and advanced line following demonstrations, including sensor value reading, error calculation, and line following control techniques. During the process we also showcased PD control and motor angle judgment, giving you a comprehensive understanding of the powerful functions and flexible applications of the MBC sensors. Now we invite you to try more creative applications yourself, making your robot smarter and more agile. If you want to personally experience the powerful functions of the MBC sensors, feel free to place an order on our official website www.axiani.shop. Don't forget to subscribe to our channel, share the video and add it to your favorites to receive more latest tutorials and application demonstrations. Thank you for watching and see you next time. You thought the video ends here? Not at all. Although I can't attend the Singapore competition in person this time, I've secretly prepared some little gifts for you. You can claim them by completing a few super simple tasks. Don't worry, no marathons required. In the next video, I'll explain the claim rules in detail, so don't miss it.